Okay, so first let me thank the organizers. I think it's a very nice workshop, and it's also very productive, I think. So today I'd like to tell you basically some very simple lessons that we have learned recently about in the context of soft theorems. And especially in particular in the case in which there are symmetries that are nonlinearly realized that involve time symmetry, so transformation of time. The simple example are boosts. And this is based basically on three works, and which are the following. By the way, I will be doing probably a bad job in giving you all the references because there are many papers on the subject, so I apologize for that, but I can tell you all the references after the talk. And there is another paper that we are finishing now, and with Lam, Austin Joyce, Ilya Komissarov, Glassman, and Yeltsin Wang. So basically the idea is the following. Let me just give you a very short introduction. I think we are all familiar with the topic that I'm going to tell you, so I'll go very quickly. I will sketch the derivation of the soft theorem. In particular, I want to focus on some details that were not appreciated before, and I want to consider just very simple example, the superfluid in flat space, and some examples from inflation, from cosmology. And I want to tell you why this is relevant and what are the motivations behind this. Okay, so as I said, I want to focus on symmetries that are nonlinearly realized, that involve the transformation of time, and boosts are an example, as we know. So, and these symmetries are very common, if you want, in cosmology, but also in condensed matter systems, okay? For instance, the superfluid, but also we have many other examples where Lorentz symmetries are spontaneous, like solids and so on. So let me just remind you that so soft theorems arise all the time. So every time you have a symmetry that is spontaneously broken, and the most famous example are Weinberg's soft theorems. Basically, the idea is that, as we know, if you consider scattering amplitude that involves a soft particle with other n particles, this is related to the scattering amplitude, these other particles, in a very precise way. So the soft theorems for photons and gravitons in gauge and gravity theories. This is something that we know very well. The Adler zero is another example. So basically, if you try to scatter shift symmetric scalar fields, the amplitude goes to zero if one of these scalar is very soft. So if it has a momentum that goes to zero. And another example, so another reason why these soft theorems are relevant is because they can be used as an organizing principle for effective field theoretism. And in the cosmological context, which is the topic that I'm mostly interested in, soft theorems gives rise to consistency relation. So let me just emphasize the difference between a linearly and non-linearly realized. So the idea is basically very simple. So for a symmetries that is linearly realized, so if you act with a certain operator, let's say on a correlator of this form, zeta k1, zeta kn, okay, the sum over I from 1 to n, you have this kind of correlator. And this symmetry is linearly realized. Basically, this object is zero. For instance, if you take spatial translations where this L is basically Ki, then it's clear that linearly realized spatial translations basically means momentum conservation. Okay, this is something that we know very well. Now, instead, let's consider a symmetry that is non linearly realized. This object now is going to be different from zero. And in fact, this is basically the word identity. This is basically the consistency condition. The most famous example is that is the Maldacena consistency condition. If we take the soft limit of the 3-point function in cosmology, this is basically related to the 2-point function, so the product of two power vectors. Okay? And S tells us what is the deviation between exact scaling variance. So this is the most famous example in cosmology of the soft theorem associated with the spontaneously broken dilations. Okay, so this is a very short summary of the examples that we are familiar with about soft theorems. Let me mention very briefly why they are important. So, why soft theorems are important? The first reason is because they are general and model independent, and also they are exact and non-perturbative, can be exact and non-perturbative in the sense that, so in this sense, this means that they are very useful, for instance, when we talk about large-scale structure or objects that are very, very nonlinear, so in a nonlinear regime, okay? And also another important point is that they are they allow to connect directly with the data. We don't need a Lagrangian. This is something that is purely based on symmetry. So they provide a direct connection, if you want, with the data. So in this sense, they are very powerful. And last, let me mention that they are not empty statements. In the sense that the Maldacena consistency condition can be violated. So it relies basically on having a single clock attractor cosmology. So whenever you violate the single clock or the attractorness, basically you this does not apply. In fact, I want to emphasize that it's possible to derive different types of consistency conditions in Alpha-Svarov, and where the soft theorem is very, very different from this one. Okay, and that is an example in which these time symmetries appear, play a crucial role. Okay. So the message here is that this was just a very short summary, but the message here is that despite the importance and utility of these soft theorems, there are aspects that are still sometimes not fully understood. So there are aspects that can be subtle, and we should be a little bit more careful about. Okay, and I'm going to discuss some examples in this context. Yeah.
Can I ask a question already?
Yeah, sure.
So you're saying that there is direct connection with data, but within cosmology, the definition of the soft modes can be a bit ambiguous, given the finite size of our universe, so we can confuse the large-scale modulation by some background effect. So the concrete example you gave of the soft theorem precisely gives a prediction that is not observable.
Yeah, so I agree. Yeah, totally.
It's not a connection with the data, actually.
No, yes, of course.
Be sure that for each of your conclusions, should you check at the end that it indeed leads to an observable?
Totally, I agree. In fact, there are subtleties that I didn't mention about the observability of the soft limit. In fact, yeah, exactly. I agree with that. I was a bit quick, but what I meant is that to derive the soft theorem, you don't need to specify a Lagrangian. You don't need to stare at a Lagrangian. You just have the symmetry, which is based by basically observations. We have some indications that tell us that the early universe is based on basically it should be very close to being a de Sitter space, for instance. We know what the isometries are, which are spontaneously broken because there is a deviation from scale invariance, and just from the symmetries you can write the relation among observables. Of course, there are subtleties about observability and at which order you can observe this relation. I agree with that. But notice that this is also depends also on the type of software that you write down. Some of these aspects are different, are going to be different for out-of-row role and for different types of consistency condition that you write down. But we can discuss later. So basically, the motivation of this talk is to address these more subtle cases in which the standard derivation of the soft theorems that do not apply. In fact, one of the messages is that sometimes the best you can do is to write down consistency conditions that involve operators at different times. So this is an equal time consistency condition. Sometimes you cannot do that. The best you can do and hope for is to have a different type of relation. And the other message is that you would like to see the consequences of the features of the breaking pattern at the level of the correlators, and I will show you that there are some funny things that can happen if you try to reconstruct the breaking pattern just by looking at correlators. Okay, so let me now just give you a sketch of, let's go together through the derivation of the soft theorem. Let me highlight what are the aspects that are usually, that are a little bit subtle when you consider a time symmetries like boosts, for instance, or different types of time symmetries. And for simplicity, so for simplicity, I will focus on in correlators. Of course, we can also talk about in-out correlators. I will say something probably at the end, but this is what we are interested in cosmology. So this is what I will be focusing on. Okay. So basically, we are interested in computing the expectation value of some operator at certain momenta K1, Kn in sandwiched between the in vacuum. And this O can be and will be typically the product of, let's say, of some generic field phi, this momenta K1, Kn. And now the assumption that there is a symmetry that is spontaneously broken is basically the fact that there is a commutator with the charge that generates some symmetry. Okay. Now let's go through together the standard derivation. At this point, what you do is basically you say, well, let me do the following. Let me take the expectation value. Let me sandwich this with the initial vacuum. This is what you do, okay? And now the idea is, well, let me also do something else. Let me insert a complete set of states. So basically, we want to insert here a complete set of states. Okay? That's basically the standard idea. Now, let me emphasize that this is basically the eigenvalue associated with the field operator. And this I means that this field is computed at the very early time where we know what the wave functional is. Of course, this field can be in principle computed at whatever time you like, but this might be complicated to know what the wave function is. In fact, usually there are interactions. So in the initial vacuum where everything is Gaussian, we know what the expectation value is, how this charge, if you want, acts on phi. So in the end, I will skip, of course, the derivation, but let me tell you some detail. So let's write down the most general, the expression for the charge. Okay, this is, as we know, the integral into x of the zero component of the nether charge, and this can be in general the following form. Can be some that can be a term that is proportional to the field itself, and there can be a term that is proportional to the conjugate field, okay? And this is the piece that we are usually familiar with. The message here is that there are situations in which there can be a contribution that is proportional to the field itself. And this is the new part that, if you want, it sometimes is not taken into account because it doesn't play a role. It does not play a role, for instance, to derive consistency conditions like this. But if you have time symmetries, there can be a contribution when you compute the nether current. When you compute the nether current, there can be a contribution coming from a boundary term, and this is basically where this term comes from. And this is the case for time symmetries. If you try to I will give you an example, but if you consider, for instance, boosts for a superfluid, then you will have a contribution like this. Okay. Now we have the expression for the charge. You can write the charge also in, if you want, in Fourier space. This is basically going to be the soft limit of this alpha, if you want, the field, some time q. Let me also put the time, the initial time. These are just definitions, basically. These are just Fourier transforms of these arbitrary coefficients that depend on the symmetry. You give me the symmetry, I know what this alpha and beta are, I know what this alpha and d are, okay? Okay, so again, I will skip the detail, but the idea is basically just take this, give me the symmetry, compute these parameters, write the charge, plug it here, insert a complete set of state, and you derive an expression that I'm going to write down very, not in detail, but I want to comment on some of the important aspects, which is the following. You will find the following stuff here. Plus some complex conjugate. I will not enter into the detail, but I can tell you if you want, and this is going to be equal basically to the expectation value of the linear transformation of this operator sandwiched with the in vacuum. So again, let's forget about the detail, but these are the messages that I want to leave you. First of all, notice that this is a relation between some n+1 point function and an n point function, which is basically what we expect from a soft theorem. Notice that this epsilon is nothing but a function that comes from the vacuum wave function. In other words, if you are more careful, you will need to compute what is this vacuum wave function that is going to be basically proportional to the the exponential of basically the integral of this normalization, if you want. Something like this. So basically, this means that in the at early times, you know what the wave function is. It's going to be a Gaussian. There will be some normalization factor, and this normalization factor is basically what appears here. So this is given. This is something that we know. Okay. We know also this alpha 0 because we know the symmetry. We know this because we know the symmetry. So basically, this is the relation between an n+1 point function and n point function. Let me also comment on something else. Notice that, as I told you, we inserted a complete set of states at early time. And the reason is because we know what basically the expectation, we can compute, in other words, this quantity. Okay? That's basically the reason. In fact, this is not a familiar, in some sense, n+1 point function, because this soft mode is at early times, while this operator in principle is at late times. And in fact, it can even be, the situation can even be more general, because with this O, with this field, you can even put these fields at different times. That's not a problem. The only main aspect is that the soft mode has to be at early times in order for this derivation to go through. Okay. Now the question is, another observation that I want to make is that can you always promote this soft mode to late times and obtain something like that? For dilation for inflation, the answer is yes, but sometimes the answer is no. And this has been what are the assumptions and what are the aspects associated with that have been discussed in a paper by Lam, Austin, Joyce, and Wong here. So you can check the reference if you want, or you can ask Lam, or I can tell you also something. But basically, the idea, the message is that in order for this relation to be valid at late times, what you want to do is basically to evolve this guy from initial to late time, this object from initial to late time, and also this object. So, and not always all these time dependence cancel among these three objects to give something that is basically the same expression evaluated at late time. So there are some aspects that are subtle, but the message is that sometimes there are cases in which this relation is the best you can do. And one example is precisely the case of the superfluid, okay? Which I will tell you now. Other questions about this? So let me talk about the superfluid. So a superfluid from a quantum field theory perspective is basically a system with a U1 symmetry that is spontaneously broken in a state at finite density or a finite chemical potential mu, associated with a conserved U1 charge. And it can be parameterized, the breaking pattern can be conveniently parameterized in terms of a scalar field, let's call it phi again, that takes an expectation value, a non-trivial expectation value plus the equations. And these are basically, these pi parameterizes phonon excitations in the superfluid. So, and the Lagrangian, the EFT for the superfluid at low energy is basically a generic function of x, as you know, where x is pi squared. And this theory realizes non-linearly three types of symmetry. There is, of course, the Xi symmetry that acts on pi in the standard way. There are time translations which act on pi in this way. Okay, and there are boosts. Of course, everything has to be contracted with some infinitesimal parameter here. Okay, and basically, yeah.
There is something with the homogeneity of the second one.
What do you mean?
The left term is not homogeneous to the right.
The left term, you mean in terms of dimensions?
Maybe it's a dot on the left hand side.
This is a dot.
And on the left also?
Here?
Yes.
Well, yeah, you have to be careful. Yeah. Yes. Yeah. Let me check. There's a delta t. There is a delta t. Yeah. Yeah. You can put an epsilon if you want. So, well, and so the idea is the following. Now, can we write down, we have the symmetries, we can basically take the symmetries, go through the standard derivation, write down the charge, and check that in fact that these expectations, but these sort theorems are satisfied for the superfluid. In fact, if you take the time translation, this type of symmetry is basically kind of trivial. You just check that this is satisfied. The first observation that I want to make is that for time translation, you can also write down this identity at late time. So you can just promote this initial field to late time. And in fact, the assumptions that are discussed in this paper are satisfied. But not for boosts. For boosts, basically, the best you can do, as far as we know, is to write down a consistency condition, a soft theorem like this, where the soft mode is only in 30 times in some sense. Of course, these observables are kind of peculiar because we are talking about the superfluid in flat space. The idea, of course, is we want to go in the cosmological setting, okay? Where everything is very, it's clear what we're talking about. But at least the superfluid is a very simple example that allows us to, yes.
This is where you're writing the formula, the master formula, right? Is it assuming that there's only one independent field that transforms non-linearly, or does it account for as many as you want?
Well, in this derivation, we are assuming that there is just one field, but in principle, you can write down more general soft theorems with multiple fields, assuming, for instance, that the other fields transform linearly under the symmetry. It's not a problem. You can just you can go through. There are slightly different manipulations that you need to do, but it is in principle possible. But then the connection with observations is another thing, but in principle you can. Another point that I want to stress is the following. If now we consider boosts, and you check this symmetry, you check this consistency condition, somehow it's kind of funny that this is trivially satisfied. So it becomes an identity of the type 0 equals 0. And let me tell you why this sounds a little bit curious in the following sense. We know that if you take this Lagrangian and you expand it in Lagrange, and you expect something that is that you expect something on the following, and you expect that the operator, as we know very well, pi squared, and the cubic operator pi dot di pi squared, have coefficients that are related, and the relation is dictated by the spontaneous breaking of boosts. Somehow, the soft theorem is completely, so this information is completely invisible at the level of the soft theorem. And this is kind of puzzling, because the question is where is this information stored? Okay. Well, the answer is that you have to consider different types of correlators. One simple possibility to see that to see what is the consequence of boosts is to take this operator, for instance, at two different times. Let me be more specific. So imagine that I want to start with the most general action of this form, where I put the pi dot squared. I put so this is the quadratic part of the Lagrangian. And let me consider a situation in which I consider two coefficients, C1 pi dot cube plus C2 pi dot di pi squared. We know that this coefficient is completely arbitrary, but this coefficient is fixed by the spontaneous breaking of Lorentz symmetry. Okay? This is something that we know. In particular, we know that this C2 has to be equal to CS squared minus 1. So how do I recover? And if you take this action and you try to compute explicitly this correlator, you find exactly 0. So it seems that this information is not contained in the correlator. In fact, what you have to do is to consider different type of correlators, in which, for instance, this object is at two different times. Or you might even try to compute, instead of phi, you can take the conjugate field. So what is the message here? And of course, I've been talking about the superfluid, but all the words that I've been saying apply to some extent also to the EFT of inflation. So the question is, again, imagine that this is the simplest prototype for the EFT of inflation. I'm talking about flat space, but we can write the same action for an FRW cosmology. And the question is, where is this information stored? It's not stored, it doesn't seem to appear from standard soft theorem, and nor it doesn't seem to appear from a correlator, equal time correlator. So you have to consider this more complicated structure in which this object, for instance, is at two different times. So this is one of the messages that I wanted to tell you, okay? Let me give you the other example. How much time do I have?
Well, a few minutes in principle.
Okay.
5 minutes.
Fine. Okay, sure. Let me tell you about another example, which is ultra-slow roll. So the simplest realization of ultra-slow roll in cosmology is basically the following mechanism, but the potential is exactly flat. And in fact, the equations of motion are kind of trivial. And the slow roll parameter epsilon is very small, 8 is basically -6. And
what do you mean by ultra?
well, the potential basically is the potential is exactly flat. You're not dropping phi double dot. You have different type of solutions, And in fact, if you check these little parameters are slightly different. Eta is not small. In fact, it's very large. So this is a different realization. In fact, this type of cosmology does not satisfy the Maldacena consistency condition, even though it is a single clock cosmology. And the question is, what is the analog soft theorem for this type of model? So what are there soft theorems for alpha-slow? And the answer is yes. And this is another example where time symmetries appear. In fact, we can consider the following. Notice that this is a symmetric theory, and you can ask the very simple question: can we check whether a symmetry is a plane yearly universe, or can we write down a soft theorem for a symmetric cosmology? Okay. And symmetries, we like the symmetry from the bottom-up perspective. We know that it's usually used to argue about the radiative stability of the potential. From the top down, we have many examples from string theory, axial monogamy. So typically, we like the symmetry. But the question is, can we check it? Can we check at the level of the observables? Do we have some consistency condition? Okay, and the answer is yes. In fact, what we have shown in these two papers is that the standard symmetries that we usually use to derive the Maldacena consistency condition, the standard adiabatic mode, the soft theorems, can be combined with additional symmetries, in this case a symmetry, to derive a more general class of soft theorems, which are in the end the late time version of what I've been writing here. Okay, and in fact, for alpha-slow roll, these symmetry look like the following. They are residual large diffeomorphisms of the following form that look like some sort of time-dependent dilation, and the symmetry that acts on zeta is of the following type. Okay. And this is the new part compared to standard dilations in cosmology that give rise to the Maldacena consistency condition. So if you want, this is basically the adiabatic mode for alpha-slow roll. Okay? And if you go through, if you take this very general result, apply it to alpha-slow roll, you extend, you check the assumptions here if you want. You extend the initial soft mode to late times. What you find is the following soft theorem. Equal to 6 PQ, which is very different compared to the Maldacena consistency condition, as you can see. And this is basically, is in agreement with the explicit calculation that you can do from this Lagrangian. For instance, compute FNL, and you find FNL that is equal to 5. So in other words, the message here is that, again, as you expect, if you know the symmetry, you can write down a generic relation at the level of the observables without doing any calculation. You just have the expression for the general expression, you just apply the symmetry. Okay. And okay, let me summarize because I think I'm running out of time. And so the first aspect that I wanted to tell you is basically there exists a larger class of soft theorems, and in fact sometimes these more general soft theorems are the best that you can find, and some of the properties, some information about the breaking pattern is hidden in these more general soft theorems rather than in standard equal time soft theorems. And the other message that I wanted to leave you is that if you use these general soft theorems, you are careful about, especially in the presence of time symmetries, you can write down a soft theorem for more general than, so for different types of cosmology that do not satisfy the assumptions of single clock and attractor. And for instance, in the case of this very simple realization of ultra-Taylor, this is the soft theorem that you can find. Okay, let me just conclude with some open questions. Probably there are more questions than results. Today I will tell you more, leave you with more questions than results, but I guess this is the spirit of the workshop. So recently there has been some progress in trying to reconstruct, if you want, the correlation functions, the cosmological correlation functions directly on the future boundary of the sitter. So this is the spirit of the cosmological bootstrap. And in some sense, one aspect that remains to be, I guess, completely understood is the consequence of nonlinearly realized symmetries. So one question is whether this is to what extent this is useful and can be implemented within this cosmological bootstrap program. And in particular, try to see, for instance, how to define the EFT of inflation directly at the level of cosmological correlators. The other question that I wanted to leave you with is that do we have soft theorems for scattering amplitudes when Lorentz symmetries are spontaneously broken? I mean the following. We know that, for instance, I told you about the Adler zero. The Adler zero is true in if Poincare is not broken. Basically, it follows from the fact that you cannot write down any trilinear interaction that is a sheet symmetry for the scalar field. But if Lorentz is broken, in fact, you can write down pi dot cube and pi dot di pi squared. In fact, I told you that the coefficient of this operator is fixed completely in terms of the sound speed. Okay. In fact, if you check the Adler zero for the superfluid, where Lorentz is spontaneously broken, you find that there is a non-trivial 3-point amplitude. So, one phonon decay in two other phonons, which is basically -6 alpha I omega 1, omega 2, omega 3, where this alpha is basically the coefficient of this operator, while this is 1 minus c squared, okay? And in fact, this is non-zero. And in fact, you can check that if you take the soft limit of a 4-point amplitude, this is not, this is proportional to this A3, which is non-zero. So there is no Adler zero for the superfluid, okay? The point is that this soft theorem goes in some sense in the opposite direction that you would have expected, in the sense that the coefficient, that this proportionality constant is basically alpha. So the coefficient, the coupling of the operator that is not fixed by Lorentz boosts. This coefficient is fixed by the spontaneous breaking of Lorentz boosts. So this is kind of the opposite of what we see for correlators. Basically, the question that I want to leave you with is whether we can find the consequences of this type of soft theorems at the level of scattering amplitudes. In other words, can we write down some non-trivial soft theorem for scattering amplitudes where we recover this relation? The relation basically between this operator and the sound speed, or and all the other relation, because there are similar relations among at all orders in perturbation. And the last question probably that I wanted to mention, of course, this applies also to, can be generalized to special conformal transformations in cosmology and different types of condensed matter systems. The last question is, how about memory effects? So, this is something that we have been thinking about. So we know that there are these nice connections between soft theorems, asymptotic symmetries, memory effect. Do we have something similar for even in flat space for this type of condensed matter system like the superfluid. Okay, so I think I should stop here. Is that right?
Yeah.
Okay. Thanks.
Thanks a lot. Okay, Jan, maybe, and then.
In the DFT for the superfluid, we have a shift symmetric scalar, but the amplitude do not vanish if the limit momentum go to 0. So why? How can we explain this?
Yeah, in fact, it is funny because the reason, formally the reason is what I said before, is that you should expect the amplitude to vanish, so you should expect that typically the average 0 is telling you that if you take the limit that you going to 0 of a certain amplitude, with a soft insertion, this is going to go like Q to the sigma, where sigma is larger than 1. And if Poincaré is not broken, this follows from the fact that you can never write down a trilinear vertex. If Lorentz is broken, in fact, you can, and this conclusion does not apply. In practice, what happens is that your question is that now each derivative carries one qubit, carries one momentum. One of these fields is a soft, so you have a certain Q that comes from one of these fields. Why doesn't it go to 0? Okay, the reason is because this Q multiplies something that has a pole. So this Q cancels with the pole, and in fact, there is a non-zero contribution coming from parallel Q.
A question?
Yeah. Thanks for the explanations. About this soft theorems, is there some implicit assumptions in the cosmology about the slow time dependence on the background, or some kind of adiabaticity conditions that you don't have transient violations of slow roll or stuff like that? Because
you don't have what?
Transient violations of slow roll, or let's say the smooth dynamics of the early universe, because in that case you would expect even in the squeeze limit, for example, of the pre-point function to have very non-trivial behavior that can be mimicked by a simple ns-1 thing, right? Like you have oscillations, etc. So maybe just my point is that maybe by going to the infinitely soft limit, like Q really 0, you will recover the result you're quoting. But is there a way to check how deep into the IR you should go in order to recover this result? Or if you want Q is a dimension full quantity, you say Q goes to 0, but maybe I should compare it to another scale to know how small it should be.
Well, typically it has to be smaller compared to the other momentum that you are considering, but you want some number. You want to know how small this ratio Q over K should be. Is that right? Well, let me try. I will probably not answer directly your question, because I think one possible interpretation of your question, if I understand correctly, is whether I should have to be careful about the evolution, the time history of the background. Is that right?
Yes, yes.
So, and sometimes the answer is yes. For instance, in the case of the Maldacena consistency condition, that is pretty that is truly model independent, I would say. Something that I didn't mention is that this type of soft theorem is not as model independent as the Maldacena consistency condition is, because if you are so this applies to the simplest realization of Alta-Zolorov. But if you try to consider a more general version of cosmology of Alta-Zolorov, in which for instance, you consider just a P of X theory, in the Alta-Zolorov case, you will have this 6 is going to be different. So, in fact, it will depend on the background evolution. So there is some model dependence here. It's not as model independent as the Maldacena consistency condition is. So to answer your question, I'd say yes, you have to be careful sometimes about the background evolution. But you can still find, so let me try to say once more. If you give me the symmetry, I can always write down the soft theorem, okay? Sometimes I also need to know the action, but that's it, not beyond that.
Okay, so maybe assuming the symmetries, already amounts to having some assumptions about the background not being crazy, or not?
Well, so you for sure you need the symmetry. I just want to say that that sometimes I need to know what the action is because the information about the evolution of the background is going to enter here.
Okay.
Okay. No other questions?
Yeah,
Yes?
sorry, so that sort of limit, is it the same thing you were getting here in the sense that one of the fields has to be evaluated at early times?
No. Well, in principle,
So that's at late times then.
everything here is at late.
So do you have a version of this there?
In fact, the most robust soft theorem for ultra-low has to be written in this form. Okay. Now, for ultra-low in simple realization of ultra-low, the assumptions of this paper hold, and you can check that you can write down the soft theorem at late times. There are different realizations of ultra-low in which the sound speed depends on time, in which this is the only thing that you can write down. In fact, in these more complicated realizations, the assumptions of this paper do not apply.
This is assuming that you're always in ultra slow roll, not that one of the modes.
Yeah, I'm not, again, exactly. I'm not, in principle, I have to be careful about the evolution, because this soft theorem is sensitive to, it has some model dependency. So it is sensitive of, it depends on the background evolution. So if you have some transitions, the answer is yes.
Okay, so you cannot continue, I mean, you cannot say, okay, I have an epoch of slow roll and then I have a transit of ultra slow roll and see what will be the soft limit.
You have to be careful, yeah. You can do that, but you have to be careful.
Okay. Good. So thanks a lot again.
Thank you.
And go for lunch.